Hi, everybody. We're back. And today we're going to talk about software architecture. In particular, we are going to discuss what untranslatable metaphor has asked about a mere 3 hours ago. And since we've gone over object-oriented programming, could we do a deep dive on that, or software architecture? What is software architecture? What is the goal of it? What role object-oriented programming plays in SA? And how to know whether some app has good architecture. Okay, these are all fantastic questions, and they're very complicated to answer. This is going to take a while. So I spent a little time thinking about how to break this down. And what I'd like to do is start with software architecture. Try to understand, what does this phrase mean? Why does it matter? And when should we think about or use software architecture? And this is a good video for drawing, I think. So I created this new sheet for us on OneNote to draw some pictures. I think that will come into play. But let's start with software architecture. And I meander, as I think many of you know. And as soon as I started looking at software architecture, my mind immediately went to the notion of architecture just in general, especially hardware architecture. And then I kind of went a little bit down this rabbit hole of microarchitecture, this thing. And keep in mind, my background is I love both software and hardware equally. I'm more of a software person. And part of that is building software, I think, is just easier. It's faster. Your iteration time is much shorter cycles. But I was at Intel for over a decade because, my master's and my doctorate are in computer engineering, not computer science. And that was on purpose, is I wanted to know more about hardware. And I felt like I understood software pretty well. Like, again, I don't know that anyone masters software, but I wanted to understand hardware more. And so the way I think about these things today is very much like a symbiotic relationship. And I realize I might be in a minority here, but the folks that I hang out with, I think they tend to see things in maybe a similar view. Folks like Alvin Chung, Professor Alvin Chung out of Berkeley. I think he used to be kind of like a hardware guy, and now he's more of a software guy, but he thinks about both. I think about Professor Azalia, and I can't remember how to say her last name, so I won't even try. But she was at Google Brain. I think now she's at Stanford. And I know that she uses software and machine learning to do hardware generation. And so there's like a growing community. There's this concept called software, hardware, co-design. Sorry, it's just taken me a second to figure out if I haven't written that word in a while. I usually just write the word design. So co-design. And the idea here is that hardware and software are sort of connected. They're what you can achieve with software is predicated by what is available in the hardware. And depending on who you talk to, you'll get different answers to this question. But I don't know if I'd say a strong conviction on this, but I have a conviction on this. And the question is this: which one of these two things dictates the other? Do you build software to leverage what is available in hardware, or do you build hardware to leverage the things that you can do or that you want to build in software? So which one is influencing the other? And at the surface, depending on, I think a lot of people would look at this and say, oh, well, you build hardware to embody the software that you want to build. And I think that this is generally the view that I take, is oops, I accidentally pressed a button there. The hardware is built to support the things that we want to build in software. Now, there are other people that, and there is some validity to this argument. There are other people that believe you should expose what is possible at a hardware level, and then when you build it, the software folks will find a way to utilize it. And the reason for this argument, just to be clear, which in my mind is logically sound, the reason for this argument is that hardware lives in a physical world. Software lives in a virtual world. The virtual world is essentially boundless. There's no limit to the creative ideation that we can have in terms of software. That's why when you look at this definition of software architecture, they say architecture of a software system is a metaphor. That's because it's not a real architecture like architecture of a building or of a house or of a processor, because those are physical things that exist in the physical world. And because software is virtual and it's boundless, the possibilities are endless. So, what dictates or predicates what's possible in software is what's possible in hardware. And this is why I make the argument that where we're going with AI is largely economically infeasible, because it doesn't matter how big you can build these language models in the software space, because this is a virtual world. We can make these things as ginormous as we want to with software architecture because it's not the real world. But software has to run on real world physical hardware, which does have to follow the constraints of the real world and has physical properties that must be obeyed based on the laws of physics, like thermodynamics. Otherwise, things just won't work. And one of those things is like capacity of transistors in microarchitectures. And it's also things like heat dissipation, which again is a physical world problem. Software world doesn't have to deal with things like heat that's generated from hardware architectures or hardware embodiments, but hardware systems do. So under that premise, there is a very real argument that the hardware designs should exploit as much as physically possible. And truthfully, I think this is part of what NVIDIA did, is GPUs have exploited what is possible from a GPU perspective, graphics processing unit. sometimes referred to as a GPU, general purpose graphics processing unit, but today more commonly known as just GPU. I'll write that down. And graphics processing unit. Now you get to feel the pain of what my students have to suffer through with my terrible handwriting. Okay. So going back to this hardware software co-design, and believe me, this relates to software architecture. It absolutely does. It may feel like I'm meandering here, but this is critical to understanding the potentiality of software architecture and hardware architecture and software hardware co-design, which is generally an architectural type of analysis, right? That's generally what you're doing when you're doing hardware software co-design, or at least the times when I've been involved in it. And part of what I did at Intel was to explore these spaces. And that's part of the reason why I was at Intel for so long, is I really enjoyed working with people that knew far more about hardware than I did. And then I would complement that. I'd be like the yin to their yang on the software side. So it's like a really interesting symbiotic relationship. Okay. So those are the two views generally taken of which is more important, which architecture or which needs predicates the other. Is it that what we need in software then determines the next generation of hardware, or is it what is possible in hardware and we build it and then that predicates what you can build in software? Both of those arguments, I think, are valid. And in fact, at Intel, there were a large group of people that thought you should just build everything you can in the hardware, and then software people would figure out how to use it. Just make it available to them, and they'd figure it out. Some people thought this was a bit reckless. I think it depends on how advanced the software people are. For people like my group of friends, I think they would love this because they would have a field day with it. But are all software engineers out there, so deeply in tune with software and hardware that they understand how to exploit the hardware, like at a micro architectural level? Probably not. So this was one of the main arguments of why you wouldn't do this. Okay, so the higher order bit, the reason why I'm harping on this is that when you think about architecture, there tends to be at least two main types of things that you think about with architecture for at least the hardware and software space. And that is the overall architecture and then this thing called microarchitecture. And it looks something like this-ish. I'm not drawing this exactly right. Let me try again. You can just call it UArch. So you can write it like this, or you can write it like this. Except there really isn't a letter in the English language to write it this way, to write it this way. So most people just write it this way with a U. And I just want to mention this very quickly. Architecture, Flynn's taxonomy. Maybe we'll get into this. I realize this is deviating from software architecture, but again, trust me, the whole symbiotic relationship part is critical. And then here you can see computer engineering, microarchitecture, also called computer organization. I really don't love this term, but it's true. Sometimes abbreviated as UArch. This is the thing that we kind of have a difficult time writing in English, but we can write this one. So if you see this, now you know that this basically just means microarchitecture. So now, like a scary term that you might not have known before this GTT episode. If you get nothing else from this episode, hopefully you learned this one tiny thing, and the world is maybe a little bit less of a scary, crazy acronym world. Because I remember when I first saw this, I was like, what is this thing? And again, most of these little secret tribal terms, they're not anything special. They just require us to dig down the rabbit hole a little bit. And then they're used just because microarchitecture is a long word. And so people are lazy and they want to just write the shorter version. So UARC is much shorter, right? Okay, so here's an example of microarchitecture for hardware. Let's not get too far down this rabbit hole for this episode, and then more stuff and more stuff and more stuff. And if you do a degree in computer engineering, you'll get into this stuff. If you're just more software oriented, maybe you'll know about this like a little bit, but not that much. Okay. Now let's go to software architecture. And we'll just read the formal definition we have on Wikipedia, and then we're going to talk about this the way that I think about it. And I'm going to move away from things that I think are very formal and try to give an intuition on why I think software architecture is important, when I think it's useful. And then there are very particular cases when I think it's when we should use it, why it matters. But first, we should start with like what exactly does it mean? So software architecture is a set of structures. Again, very similar to hardware architecture. It's structures that are needed to reason about a software system and the discipline of creating such structures and systems. Each structure comprises software elements, relations among them, and properties of both elements and relations. The architecture of a software system is a metaphor analogous to the architecture of a building. It functions as a blueprint for a system in the development project, which project management can later use to extrapolate the tasks necessary to be executed by teams and people involved. Yes. Okay. Software architecture is about making fundamental structural choices that are costly to change once implemented. True-ish. This is one of the main reasons of why it matters. Is you will think about software architecture before you implement something, because once you start implementing it a certain way, changing it can be challenging, which is also why you generally want software systems that are iterable and adaptable. You want software systems that are iterable and adaptable. Critically important. The reason why you want them to be iterable and adaptable is you're going to get this wrong. You're going to get this wrong. If you think you're going to get this right, you haven't built enough software systems to know that you're going to get it wrong. For someone that has been doing software for 30 years, I have millions of lines of experience of writing code to demonstrate that no one gets this right ever. It's not possible. And the reason why is that software evolves. Software, when it's used, by definition, is going to tend toward increasing entropy, because we're going to add new features, we're going to add new functionality, we're going to fix bugs, we're going to extrapolate on the original idea, and therefore the design that we have today is not going to be the design or the architecture that we use tomorrow. Guaranteed. If you build a large scale system that people use, that original architecture that you had in version 1, not going to be, it's going to change. And if it doesn't change, then what you're likely going to have is a dinosaur. Something that it was super powerful at one point and now it's completely gone out of fashion and it's just not useful. Prime example, not trying to pick on this company, but yeah, I guess they don't care. They don't exist anymore. Blockbuster Video. Their architecture was VHS tapes. That worked. They did not iterate and adapt on their architecture solution. In this case, it's software, but again, remember the symbiotic relationship between software and hardware. In this case, the software would be the movie, the hardware would be the VHS tape. This thing is not evolving. This thing is. And so then you migrate away from this, and the hardware system now is no longer a VHS tape. It's a computer. It's the cloud. It's the server, and it's the internet. That's the hardware system. And that software system, so some of that is the hardware system. That's like the cloud. I guess software system is, the internet is both things. It's hardware and software. And then the actual movie is now changed its medium to be more digital, right? And therein goes back to the point about iterable and adaptable. If you take one thing away from this episode, it should be that the software system that you're building, the software architecture you're building should be designed in a way that it's easy to iterate and adapt, because you're going to get this wrong. If you build a sufficiently large system, and I'm not talking about toy systems, right? And I don't mean this as an offensive thing. I mean, as I've said many times, any system that's basically under 100,000 lines of code, I think is not really like a real system. It's not a system that I think is going to like be disruptive in the world. It's not that it won't have value. Like, I know many libraries that are less than 100,000 lines of code, like my tree library, and it's valuable, but it's so simple that I don't even know that you need to have a software architecture for it. But when you get into bigger software systems, like I can imagine Uber's ride-sharing algorithm, like the geo location of the vehicles and the passengers, insanely hard problem. And it gets harder as that problem scales. And now not only are they doing ride sharing, now they are delivering food, and in some cases it's moving to like actual goods outside of food. Like I think I'm starting to use them to deliver electronics now. So like cables and small electronics. I don't think I've ordered like a TV or anything from Uber Eats yet, but they're moving in that direction. So you can see that this is what happens when you build a software system that is ubiquitous, that has tremendous value, is it just continues to evolve. I think one of the jokes that I had for a long time is that Apple's iTunes app was a terrible name because it did far more than just tunes. It did all kinds of things. And I think maybe they've renamed it. Maybe they haven't. I'm not sure. But the point is that iTunes started out and it was just music. But they did such a good job, as Apple tends to do. Then it was like, well, we can do videos. And then we had this whole app revolution. Now, keep in mind, this is before there was the App Store. Okay, this is for those of you that are old enough. There was a time where you had iTunes as a store, and that's all you had. The iPhone didn't exist yet, guys. Okay, there was no App Store. It was just iTunes, and then iTunes was the precursor for Apple's App Store. it started as this and then it evolved. And then it was like, oh, wow, there's going to be this whole ecosystem. It's not just about music. And gee, we should build a phone, and a phone should have an operating system. And then we should have this whole ecosystem on the cloud that does more than just music. It can do applications, it can do videos, it can do all this stuff. And then that is maybe where it is today. And I think that's a prime example of what I'm talking about here. Is this is why you want the system to be iterable and adaptable. And I realize that for some new programmers, this might be a concern that's far afield from what you're working on today. I get it. I'm just trying to prepare you for you becoming a super seasoned software architect, and the things that you might want to be thinking about today. And if you can start to design your software in this fashion, you're likely going to get a lot more traction with your software, because once people start to use it, believe me, I've done this a few times, they're going to want new things, and you might be massively surprised, seriously surprised by some of the shifts in the direction of where your product or your software system goes. And I have many examples of that. Notica is one, Mentor is another, and other systems that I've worked on, even like Dotsa. Okay, so we have a high level understanding of software architecture, I think now. It's this higher level picture, and it's really about understanding the general structure of the software at a high level, right? Think of this as like the bird's eye view of the software. And generally speaking, you don't really think about software architecture until you are, in some sense, an expert in software development. And the reason for this is like you don't really become like a building architect until you understand all the primitives and the basic properties of buildings, right? Because in order to architect a building, you have to understand all the aspects of the building. You have to understand things like stairs and floors, structural integrity, windows, concrete, foundations, parking. There's all these things that you just need to know. And that requires a massive amount of knowledge before you can even reason about things at this higher order bit. It's similar to someone that like, and I mean no disrespect, but like someone that is going to make a minor fix to some system, like a bug fix. Junior engineer can probably do that. Software architect can do that as well. But junior engineer can probably not figure out the architecture because they just don't understand necessarily enough about software. Very much like a mechanic on a car, they can probably fix something that might be going wrong with the engine, but you might not ask them to create the new architecture for the latest autonomous vehicle from BMW, right? And so as you progress through software development, what you often find is people start at the code level, right? So we start in the code, and by the way, Taylor added visual code back in, and I knew that it was in a, whoo boy, I've got a lot to say about this. There's one issue in here that I looked at, and oh boy, I've got some stuff to say. And again, I'm not trying to pick on anybody. Guys, we have got to get this quality conundrum. I mean, like, let's just go back and look at this. Up until this point, I mean, okay, it's not great. You can see it. This might not be the best example. I don't know why the quality of visual code is so bad. I know many people at Microsoft, and they are brilliant software developers. I think they're not working on this. And I think maybe Microsoft is not trying that hard to make this software super fantastic because it potentially conflicts directly with other software that they have that's paid, right? And so if this software is super brilliant, then why would you buy the paid version? So I could see, I'm not supporting this argument, but I could see a rationale on why you would intentionally sort of not care to this is your gateway to free software, and then you level up into this thing, right? That said, this wasn't great, but something crazy is going on now. I had no idea. Literally, I just thought it was, this is probably the last time that I saw it back here in 2024. So I wasn't expecting this at all. But when I was looking at this, like, this jump is crazy, guys. I had 4,500 anomalies. Okay, so there's one that I saw in here because I was looking at some of these, and yeah, it was this one. Yeah, it was this. That's what I did. I looked at one that I thought was like sort of short and trying to understand, is Mentor wrong about this? Like, why is it, this seems like this is pretty benign. Okay, I'm not an expert in TypeScript. I want to start with this. But I spent a little time looking at this. This is, if I understand this correctly, this is egregiously wrong. This is so broken. It's hard for me even to describe how broken it is. Let me explain at a high level what I think is going on here based on what Mentor has explained, because Mentor is teaching me. This is part of how I use Mentor. This is part of how I think everyone should use Mentor. Is it doesn't just help you fix your code, it teaches you. And so that's why it explains this stuff over here before it tells you like how to rewrite this. By the way, Mentor's rewrite on this, I think, is not that great because Mentor is trying to keep the semantics intact from the original version. That's something we should probably have as a toggle. Like, don't worry about keeping the semantics intact, just make it right, versus keep the semantics intact. So right now, it just keeps the semantics intact. Eventually, we'll have like a toggle. And it'll be like, nope, just fix it the best way that you can. And it'll write something completely different. And that version probably will not include this. Okay, really quickly, what this appears to be doing is it's going to get this error message, and then it's going to use a regular expression to find the word canceled. I'm not making this up. It's going to try to find the word canceled in the regular expression to determine that this failed. Okay. If you haven't already started to figure out the levels of how wrong this is, let me start with something very simple. The word canceled. Very simple. Did you know there's two generally accepted ways to spell this word? There is this spelling, and then there is this spelling. Both canceled and canceled are correct spellings. Canceled with one L is the standard spelling for American English, while canceled with two L's is standard British English. Okay. Again, this isn't even getting to the heart of the issue here. I'm not even really laying into this code yet. Now, let me ask you something. Will this regular expression find both spellings? We all know what the answer is. It won't. It can't, because this is a complete word, and there's not this is not a subset that can find a superset of both spellings. You would have to figure out how to have a single L with a followed +1 potential L in order for this to work. But that's not even the real issue. This is me just like playing around. The real issue is this: using a message as a mechanism to determine if something succeeds or fails, especially looking for a single word in a message, is so fundamentally logically unsound. I don't know if I have words to properly express how broken this is. There's a reason why we use discrete mathematics for errors, and we use ranges of numbers for error numbers, is that the range implies all the types of errors, either for this system to fail or for some subset, some subclass of errors, like all the types of errors that can fail due to sync rebase, right? Or a fail for git publish. The reason why you use discrete mathematics, and what I mean by discrete mathematics is I mean integers that have precise meaning, is that then the way you describe that error can change, but the semantics of the error are always the same. It is timeout. Let's use timeout. Let's say network timeout is one of the errors. How do you describe network timeout? You could write 1,000 different sentences to describe network timeout. Would it make sense to search on the description of that error message as an indication of you getting that message? It would not. It would never make sense, because that sentence can change and still capture the syntax can change in an innumerable way and still semantically capture the same meaning. That's why you use discrete mathematics to capture it. You use the value -7. -7 means timeout. So you look for -7. You never look for a word, because words, as we know from natural language, they are ambiguous. We don't even have a consistent spelling of this one word. And you don't need to use the word canceled here. You could use the word aborted or terminated or a gazillion other. Just look up the thesaurus, and anybody that is running the description of these error messages can rewrite this any way that they want. The principle is they can't change the discrete numeric value that's associated with the error. That's bound. That's part of the contract. So that's what you look for. That's what you search on. No. Just no. And no. And, well, I thought there were more no's. Maybe I'm wrong. Maybe I'm just going the wrong direction. Yeah, I don't know if... Yeah, I don't... You know, I was saying in one of the episodes, like, you shouldn't embed literals in code. Like one of the reasons why you don't embed literals in code. Okay. I realize we're going off the tangent from software architecture, but this still actually relates to software architecture because how you would do this the right way would not be to embed literals in code. So here's why you don't embed literals in code. This is a literal. This is a literal string. What if the person that's using visual code does not speak English? Does this mean that they can't use visual code? No. That's why we use symbols. Like this is a symbol. And I can guarantee you that when you run Chrome in a language that's not English, when you hover over this little symbol, it shows you something other than reload this page. It shows you a string that is localized to the language of that's domestic for the user. And how do they do that? They don't embed literals in the code. They have a localization resource system that then does a translation and gets the right language. And so there's minimally like an array lookup here. And you hash on an index that is the K no stash repo. And then that looks up in the appropriate hash localized language table the right string to show. So, okay, this one you might get away with because it's a git command, but all the cases where you have like, can non-English speakers use this? The answer I would have is definitively no, they cannot. And this is one of many reasons why you do not embed literals in code. You are not building an adaptable and iterable system. And this does go back to software architecture. That's why in the former episodes, you'll see me do things like don't put those strings in there, use an enum, put the strings in some table, and then it's a little bit more work, I realize, yes, but it's creating a system that is adaptable and iterable. Like these guys are so cooked. Imagine the work that it would take to rewrite all of this. Like this is just one file, guys. Right? This is I mean, yeah. Okay. So listen, I'm going to stop picking on visual code now because my heart rate is starting to get accelerated because this I'm a missionary and I care about this stuff and this makes me angry. It makes me angry because Microsoft has enough money to not produce this kind of shit, and it does anyway. And it I don't like it. So I applaud them for making it open source, but I do not applaud them for letting it devolve into this state that it's in. Like, what is this? This is amateur hour, is what this is. I would never in a million years let code for systems that I'm writing ever have this kind of garbage in it. Never. It would never get past peer review. This is complete and utter shit, is what this is. That's just me being honest. Getting to see a little bit of the real. Okay, Goju. All right. Let's judge others less, judge yourself more. Okay. Whew. Deep breaths. Okay, let's bring it back. Okay. Again, I applaud them for open sourcing this. I do not applaud the lack of care. It makes me very sad. Because I think that it's the thing that I think it does, it perpetuates the wrong type of mentality. This teaches young people who are not experts in software engineering that this is acceptable. That's the underlying message. This is the part that bothers me the most, is like new people that haven't been developing software for a long time, they will see this and say, well, it came from Microsoft and it's open source. This must be acceptable. And then you get things like GitHub Copilot that are doing not great things. And now we get vibe coding, and just no. Dark ages. Let's not go there. Let's not go down the path of idiocracy. It has been done before. It can be done again. It could happen if we stop caring. So we got to care. Now, this does relate to software architecture, because when you try to deal with things like this, you will change the way that you design these systems. Is that what I would do? The way that Notica does this, for example, is there are no strings that get sent to these functions. Instead, there are indexes. The index covers the semantics of a message that will be displayed, and then it's looked up in a table that is customized specifically for the user to show them exactly what they need. And while Notica, for example, only works in English today, you could easily upgrade it to work in any number of languages. I just didn't have the staff. It was just me by myself. But what you can do in Notica, and what it does, is you can change all of the color systems. And it's not just this message that has a color. It's like words inside of this message that have different colors, or highlights, or all of this. You can do all this customization. This adds like tremendous amount of flexibility in the system that people might have, because they're trying to use pattern recognition to quickly parse out messages. Like, for example, over here, when I see highlighted red, I know that that's what I've highlighted with my cursor. I know that that's what this means. Also, with this code, anytime I see this purple, I know the purple means this is a program language reserved word. Like, we use pattern recognition all the time. It's super helpful. It gives us a way to process things visually in a much faster sense than if we had this all just in a single color, right? That's why we try to do this thing over here, like code words, words that are code versus words that are English language. And so, but when you do this starts to lose the ability to differentiate between something that is textual in terms of natural language versus something that is a semantic property, which is what repository means in this context. This context is related to this repository type. This context is the word repository in the English language. And you can tell because this is in the color green, which indicates that is this essential type, as I understand it. This is the actual name of the thing. This is the type. And then this is in orange because it's part of a string, right? Same word. Same word. Pretty cool how you can do these things. So this is actually part of the software architecture. Okay, let's go back to software architecture now that I've gone down that rabbit hole. And yeah, let's take a quick look at this scope just to see what people have to say. Opinions vary as to the scope of software architectures. Let's take a look at this. Wow, that really did not make it bigger. Okay. Can I increase this? Okay, here we go. Yeah. Okay. So this is, I think, a process for doing architectures. I don't think that this is like an example of an architecture. And that kind of makes sense because they're talking about like the scope of things that you should be thinking about for architecture. Okay. So let's look at these opinions. Macroscopic system structure. This refers to architecture as a higher level abstraction of a software system that consists of a collection of computational components together with connectors that describe the interaction between the components. Okay. The important stuff, whatever that is. I like this. This may feel a little hand wavy when you read this, but I actually quite like this because this is how I think about it. It is you're trying to capture the important stuff, and that changes. Again, you know, I was saying like I'll try to use the simplest language that's possible, and sometimes you get stuck with words that are complicated because those are the only words that exist, like software architecture. But then when we can, we'll use things like this, like UARC, uh, to imply microarchitecture. And this is a smaller word. And then we use that not to be clever, but because it's like, oh, this is just the right word. Or sometimes we'll say things like SW instead of software and HW because it's like, it's just easier. We're not trying to be clever here. We're just trying to show that this is like the easiest way to think about it. And I quite like this, the important stuff, because that's kind of the way I think about it, is that software architecture should, like, one of the key ways that I think about it is it should try to capture the important stuff. And that changes from architecture to architecture. I'm going to show you a high level architecture of the DOTSA system in a second so you can see what I thought was the important stuff. But it's not a universal thing. You have to look at each system and contextually reason about what's important. Like a good example of this, I think, is the standard template library in C++. And when you think about containers, there are minimally, I think, 3 critical things to think about with containers. One, there is the container itself. Is it a vector, hash map, set, all those kinds of things? The second is the algorithms that you can use on those containers. Can you use sort? Can you deduplicate? Can you do one-to-one mapping from this container to that container? And what are the algorithmic options for doing these things? That's the second high-level piece. The third is iteration. Iteration is key for containers because they dictate the way that you can access and mutate the data that exists or will exist or won't exist. Insert, modify, delete. So what will exist, what does exist, and what won't exist. Iterators, by and large, control that aspect. So if I were to do a software architecture on the STL, Standard Template Library, I might start there. I would show here are containers, and there's a whole bunch of them. And then here are algorithms, there's a whole bunch of them. And then here are iterators, and there's a whole bunch of them. And they all act differently. And there's generally a binding of acceptable iterators for containers, and there's a binding of acceptable algorithms for the containers, and so on and so forth. That is, in my mind, the important stuff. But notice that that's very specific to the STL. If I was talking about things like neural networks or the way like large language models work, I probably wouldn't have iterators in there at all. It would be more about like what we drew in one of these former discussions. No, not that. What's happening here? Okay. It's up here. Yeah. So like this, I would probably talk maybe a little bit about that. Maybe a little bit about this. This is how I would start to define higher level architectures. I would probably draw this picture maybe, and then I would explain the different aspects. Okay, so now, okay, yeah, let's continue looking at these. That which is fundamental to understanding a system in its environment. This is also, I think, really important. I also think another piece that falls into the important stuff are things that are hard to understand. Things that are important but hard to understand. Because you can have important things that are easy to understand, and you probably don't need to include those in the system architecture. But important things that are hard to understand, like when I was first learning about iterators, I remember thinking, I don't know what this iterator thing is. Like, what is this? I don't understand. And somebody needed to spend some time explaining it to me. I really needed to put some hours in playing with them to grok the concept. So, yeah, I would have that as a piece. And yeah, fundamental to understanding the system, and usually things that are hard to understand. Things that people perceive as hard to change. Yeah, sure. But again, if you're following the principles, I mean, this is idealistic that you could have iterable and adaptable. As you make decisions, you will often marry yourself to certain types of components or architectures that are going to be challenging to change. So, yeah, you they're not wrong. I guess is there will be pieces that I think eventually end up being hard to change, and knowing about those things in software architecture can be very helpful because they let you know what you're essentially married to. It's saying like these are the things that are hard to change. You should know about them because these guys are not budging. You can change other stuff, but these things are like going to stay put. So you better figure out how to make these things work. Then architectural design decisions. This is I disagree with this. This is not related to software architecture. This is more of a first principles thing, and this is like it's like tenants, core tenants. These are the driving factors on why you made the architecture the way that you made it. And we do have documents like this. Like I teach first principles somewhere in my let's find this. When do I teach this? Is this? That was a fun one. I think that was actually me commenting on meeting at Linux Foundation where they're talking about introducing Rust into the core Linux kernel. Woo boy. Not how I would have done it. Separation of concerns. Okay, I think we're getting there. Did I really? Is it really that far into the course? I don't think so. I think I think. Oh yeah, this is the lecture that's missing. I uploaded the wrong lecture. I think. Thinking critical. Oh, first principles. Oh, it is sooner. Systems architecture. Cool. Yeah. So, in I think I always get your name wrong, buddy. Intractable or something metaphor. Uh, but yeah, so I talk about the systems architecture. This is when I think of systems architecture, I think of hardware mostly, but sometimes software. Mostly I'm thinking about hardware. And the reason why I talk about this for MP is that these are the things that constrain you from the in the physical world. The software architecture is far more open-ended, and so you're not as deeply constrained. So this is a bounding point, and you need to understand what this is because it lets you know what is possible and what is not possible. Like, for example, we don't have quantum computers today, so you can't use them to solve machine programming systems. Uh, we don't have some machine learning algorithm that we want to build. We just build it. We just code it, right? Okay, so uh, in this lecture somewhere, I'm going to talk about first principles, it seems, and or at least it said I was. Did I lie? Yeah, I think I lied. Sorry, guys. Maybe it's here. Okay. Maybe I intended to, sometimes I intend to get to topics and like I am in these episodes. Okay, first principles. So, first principles are the axioms or the given basically of the things that you can't kind of get. It's like what you need to have to build the stuff. Okay, so the example I use is a bicycle. Okay, so you have a bicycle and you're trying to do cool stuff with bicycle. So first principle of a bicycle. Well, first principle, it has two wheels. That's by definition, you got to follow that. Otherwise, it's no longer a bicycle. If you add another wheel, it's a tricycle. If you remove one of the wheels, it's a unicycle. So it's part of the core definition. It's a core axiom that you can't deviate from in order to solve this particular problem. If you want to solve a problem that is unicycle, then you have a very different first principle. Okay. Now, first principles help us reason about things and tell us like the range of things that we are trying to build. And also, it moves us away from being bound to solutions um, that are potentially the state of the art, but they're the status quo simply because that's just what we have. It's not that they're the status quo because they're the best possible solution. Sort of like how I feel about language models, that I think language models are cool, but is that the best we're ever going to do? Boy, I hope not. Well, why are they the rage? Because that's just kind of what we have. A first principles approach would say, how would we build machine programming systems? And then you'd be like, well, it needs to have deep reasoning. And so what would that say? Well, the basic system would probably not be a language model. So because of that first principle of needing logical reasoning as a fundamental principle, a fundamental axiom, you would not use language models as a core property of the system. It doesn't mean you couldn't use language models. You can, just not at the base level. And this is why first principles really help you, is they move you away from essentially drinking the Kool-Aid of whatever is happening today, saying we need to use their stuff because that's the way it's done, and instead goes lower and says, what is the problem we're really trying to solve here? And then it allows you to create disruptive technology. Supposedly, and I know that this guy may be not in the greatest public favor at the moment, but supposedly Elon and his crew use first principles approach for Tesla, SpaceX, and other things. And I think that at least SpaceX and Tesla are good examples of what happens when you use a first principles approach. They don't ask, like, how can we make automobiles better based on the existing technology? They ask the fundamental question of, like, what are the core properties that are required for an automobile? One of those core properties is not that it must be petroleum based. The core property, the first principle, is simply that it needs to transport you from location A to location B. That's a first principle. It doesn't say anything about the mechanism that's required to move you from point A to point B. And therefore, you can do things that are different than a combustion engine. You can use an electric engine, and then you get Tesla. On top of that, when you are building rockets, you can say that the goal of the rockets is to get into space, whatever that means. Truthfully, people have different meanings for this. If you don't believe me, Google it. It's quite interesting. And then that's it. That's the goal of the rocket. So there's this underlying principle in the rocket generation that you just have them disintegrate on reentry. And SpaceX said, well, that's not a first principle. You don't have to do that. So what if we didn't do that? Like, what if instead we tried to catch the rockets? This is the type of thing that you get when you do first principles, because the first principles tells you the core things that it must do, and that's it. All the other stuff that it does, but it's a byproduct of the technology that exists today, that is not a first principle. Those are just embodiments of people's ideations. So going back to what we were looking at with this definition over here, a set of architectural design decisions, this is not, I would argue that this is not software architecture. It does not have anything to do with software architecture. What this is a higher order concept that generally relates to first principles or core tenets. And first principles and core tenets are slightly different. The first principles are the axioms that you have. These are my attempt at defining some first principles for foundational scientific advances. Notice determinism is at the top of the list. Oh, shoot, I don't show the core tenets. I might not have shown the core tenets for a reason. Oh, look, there's iterative refinement for iteration and adaptation. Cool. Okay, so now we're through this, the scope of what we think should be covered with software architecture. And then this last sentence, there is no sharp distinction between software architecture versus design and requirements engineering. They're all part of the chain of intentionality from high-level intentions to low-level details. I think that this is true-ish. And it does make it a bit hard to understand. It's not, as many of the systems people that I talk to, what's interesting about architecture is art. It's not science per se. And what I mean by that is you can do it in a bunch of different ways, and all of those are potentially correct. Whereas when you have things that are more hard science and less art, 2 + 2 is 4. That's it. But there's many different ways to architect a calculator. That's what I mean. Okay. Now let's close by looking at an example of some software. Let's take a short pause so I can refill drinks. You guys can refill drinks and refill popcorn too. and we'll be right back. All right, folks, we're back. And now let's look at DOTSA. So here's the core DOTSA system. And we talked about DOTSA before. It's this synthetic data generator, and the core system is just these files. That's it. The challenge, though, is understanding DOTSA with just these files is really hard. You could do it, but it's not super helpful for people that want to use the system. This is where system architecture and sort of the how-to documents, I think, come into play. I think system architecture can be very useful for people that interface with your software systems. It can also be very useful for people that are going to maintain and extend your software system, which is why we generally try to produce some sort of system document for the systems that we're building, that we open source, so people can understand how it works, and then they can interface with it, and then potentially extend it, change it if they want to. So as we were talking about before, with software architecture, we start with this question of sort of what does it mean? Then, why does it matter? And when should we use it? These tend to be really, I think, good ways to sort of approach these things as far as explaining your software system. It tends to be the case that this is the most important question, the why question. However, it is also often the case that you first must answer the what question before you can answer the why question. But why is so important? Because if you don't have a good explanation on why people should care, then they won't. Okay, so here's DOTSA explaining what DOTSA is. It's this multivariate time series data generator, blah, blah, blah. Here's an example of basically the output that it generates in tabular format. And then it's going to explain the system design. So the system design in this case, this is essentially the system architecture. These terms are somewhat interchangeable. And at the time when I was at Intel, the hardware architects got a little offended if you use the word architecture when you describe software, because some of those folks were kind of the opinion that software architecture is sort of pretend because it's not in the physical world. And again, we saw the case where, yeah, it is a metaphor because software is virtual. So I can understand that. So basically, in this case, what I was trying to do is just sort of avoid a fight. I was trying to just explain the system, so I just chose the word software design, but you can use the word software architecture, and it commonly is used in the larger software community. Okay, so it talks about the software design. It has the algorithmic system, the scheduler system, and the dataset generation system. Think of how I was describing the standard template library before, saying you have got like containers, you have these algorithms, and then you have these iterators. So I start with that to give background. And then after I do that, then comes picture time. Picture time is, in my mind, the most important time. You tend to sometimes need words, though, first, because you got to kind of explain, okay, we're going to show you this, but in order to actually understand this picture, you kind of have to understand there's three fundamental pieces to this. There's the algorithmic, the scheduler, and the data generator. And so here you can see there's the algorithmic, there's the scheduler, and there's the data generator. These are the core systems of the DOTSA system. That is the core part of what you get with DOTSA. Then, so this is what DOTSA gives you. Then when you use DOTSA, you can define these pieces, and we give examples of this, and you can define this piece. So this is slightly unusual in that Datsa is designed so you can build in your own back-end scheduler, largely so you can leverage all the hardware that you have. It's meant to, again, run at scale being it's not limited really to anything. So if you have 1,000 nodes, go for it. Datsa can scale to 1,000 nodes. I think we generally kept it to a single node, but we scaled this thing to hundreds of, I guess that's more than, no, did we have some? Okay, I might need to shut up. Not necessarily because I'm wrong, but anyway, so we scaled this backend to some number of hardware threads, and it does well with the scaling, and it's designed to be extensible on the back end, and it's designed to be extensible on the front end by in the intention of the system. And now you can probably see why it's really important to explain this first. Is it's saying like Datsa itself is going to exist from having this piece, and this piece. Those pieces it has, and you can interface with them, but these pieces exist. Now, the part that I think makes Datsa really cool is the user can come in and extend Datsa in these two ways. By default, we have a bunch of different backend schedulers. So those schedulers are built to essentially help people that don't want to build their own scheduler. Scheduler is like, do you want this to be single-threaded, multi-threaded, multi-node kind of thing? And so there's a few different variants. The front end, you sort of have to do. If you don't define this, Datsa doesn't do anything, because this is what's telling Datsa that you're going to do anomalous and non-anomalous data generation, and then what the post-processing merger operations are. Like you have to give it rules and guidance on how this should be done. Otherwise, it doesn't know what to do. It's kind of like, you can think of it going back to the STL example, is the STL, they're containers and iterators, but you have to give them the data that they're going to contain and iterate on. It's the same here, is that you have to kind of tell it what the definition of your anomalies and non-anomalous data is, and then say, go generate it now. And then it'll go generate it. And then after it generates it, and keep in mind, it has it in its own internal sort of heap structure that's ordered in a way that optimized generation. So then after it's generated, you have to organize that data in a way that's meaningful. There are systems that we have as examples that do that for you, but you may have special things. So the big thing to take away is, one of the key optimizations is the Datsa system generates anomalous and non-anomalous data in generally at least in two different threads, usually two different complete systems, because they follow very different rules. So then, and you can do this completely in parallel. There tends to be no dependency on the anomalous and non-anomalous data. There can be, but you don't have to. And if there isn't, it's sort of like the optimization that transformers have over long short-term memories, is with transformers, you get away from the need to do serial training. And so the training is just so much faster. So there's one reason why we love transformers. Datsa does a similar thing, is it says you don't have to generate that data serially for anomalous and non-anomalous. You can just do it over here, and then you can run them in parallel. However, when you run them in parallel, these are all time series, or that's the whole purpose of DOTSA, right? It says like right at the beginning, it's a data aggregator for time series. So that's kind of a core constraint. And so then when you have the anomalous data and the non-anomalous data, they are time series, but they're not interleaved in the series that they would be in if they were to happen serially. So if you want them to appear in output or as input to another system, you need to intertwine them the way that they should be intertwined. You don't have to, because again, DOTSA doesn't know how you're going to use all this data. It's just going to generate it for you based on the rules you give it, and then be like, okay, cool, here you go. Here's the data. And it'll just give you these chunks and be like, here's all the non-anomalous data. Here's all the anomalous data. Have fun. And the reason why it doesn't do optimizations on this is that it doesn't want to make decisions that don't apply to you, because it would unnecessarily slow the system down. Cool. And then we give some examples on how to use DOTSA and stuff. And I think Stanley actually wrote most of this document with some small amount of guidance from me. And I think he did a really great job with this. Yeah, I'm like actually super impressed by the work he did. So just examples on how to do all the stuff that we were saying you can do with DOTSA. Okay, so that's basically all I want to share for this episode. This first entry point into software architecture. And hopefully this gives some understanding of what software architecture means, why it matters. Oh, did we talk about this? I wanted to that's right. Sorry. There's one more thing I wanted to share. There's generally two reasons that I think you want to have software architectures. There's more, but these are the two I think most important reasons. Reason number one is you are building a complex system, and you need to understand that complex system before you build it, because you're probably going to get stuff wrong. And so this is reason number one. Building a complex system, and you want to figure out the stuff that you're going to get wrong before you spend months or years building it. And software architecture can often do this. Now, keep in mind, you have to really understand software to do software architecture, because any random person can just come up with a whole bunch of boxes and stuff and just draw arrows, and it doesn't mean anything, right? So you have to actually hold yourself accountable to, does this actually represent what I'm building? So you have no compiler, right, that's going to help you. You actually have to like use this thing. And it is, I think, something that's not that hard to do, but you are going to have to be, in some sense, a pretty strong software developer before you can really start to reason about software architecture, I think, at least the way that I think about it. So the first reason that you do software architecture is you're building a complex system. The second is you are trying to understand a complex system. These are generally the two reasons why I will build or think about software architecture. One, I'm going to build something like DOTSA. And also keep in mind with DOTSA, the way I do software architecture, I figure this out first. Before I write any code, I actually think in my, and again, I'm probably an anomaly. I'm not saying that you have to do it this way. I'm just saying like this is how I do it. And if you're just starting out coding, this may not be the right path for you, because you may not know enough to be able to think in terms of code. But once you have written enough code, you can kind of just see it in your head. It's hard to explain. But for those of you expert level coders, I suspect you guys know what I'm talking about. So once you reach that level, oftentimes what I find is you can just start to see these pictures. Like, again, remember I was saying that Datsa was patent disclosure? It was it was an invention. What the invention was basically this. I said, this is what it's going to look like and do. And then the patent committee was like, oh, that's super cool. This would be awesome. Yeah, you can't build it though. This is not possible. And then I was like, okay, now let me build it so you can see. And then I built it. So I didn't write the code first. I did the system diagram and explained it. And what I do when I do these things is I hold myself accountable. So there's a certain level of maturity and sophistication that you have to do this in order to really be a software architect. And it's largely based on, like, do you really understand what you're doing? And if you do, then I think it's not that hard. You're still likely going to get some stuff wrong, but it's not going to be like you're completely wrong. Where, for example, if you're a pretty strong software architect, you could come up with an architecture for something. Like, for example, this is what my students do at the university. Keep in mind, these are all like master's and doctorate students. They will, for their MP, their machine programming project, I'll ask for, I want to know what it is they're building. I want to know why they're building it, so why it's important. And then I want to know how. What is the high level system design of what they're thinking about building? How is it going to work? And so they'll have to do this. And some of them actually get really close on this, and then they build that. Admittedly, some of the students, they completely whiff on this. They come up with a whole bunch of boxes and stuff, and it doesn't really mean anything, and then they build something totally different. This is usually like the spectrum that I'm talking about, is that you can have the software developers that are very seasoned and they can see it in their head and draw a picture like this of like, yeah, it's going to work like this, I'm pretty sure. And then it turns out that when you look at the code, it's like, oh, that's like, oh, the data set generator, oh, it's probably like this stuff. And like the scheduling system, it's probably like this stuff, right? And the algorithmic, I don't know if there's like an algorithmic file. Yeah, it's like these function and probability data events. I actually should probably rename those. But you can see almost like a direct correlation between this and this. But I wanted to share this is that what I found is it's only when you get to a certain level of mastery on programming can you start here. If you're just starting to program, you likely can't start here because this stuff won't like make sense. You have to sort of start with the code. Again, this is why you don't start building the airplane and designing a new jet or a new autonomous vehicle. Instead, you start to work on small pieces and slowly grow to bigger and bigger things. And then over time, you build up enough sophistication and knowledge to where it's like, okay, I kind of understand the whole system now. I can figure out how all of this will fit together. Like a good example of this is Urs, my chief engineer, chief architect. He can be the chief architect because he's written millions of lines of code and across dozens of different languages. So he deeply understands this stuff. And so when he comes up with these diagrams, he'll show the diagrams to me and I'll be like, yeah, I like that, but this part I'm not sure of. But it's never a question of like, I don't think that this is actually gonna, I think you're completely wrong on how this will work, Urs. Because I know working with Urs that if he sees it in his head like this, he's probably going to be 99% right. There's maybe 1% where he's off. But keep in mind, he's been doing this for 30 years. So system architecture, this is why, again, like junior software engineer, staff, principal engineer, all these things, then architect. The software architects are up here. It is a higher level position. Like, for example, Urs is both the chief engineer and chief architect, but Urs was first the chief engineer. And then after he proved that he could do all of this engineering, we promoted him to be also the chief architect. He wasn't chief architect first, he's chief engineer first. In my view, the architects, this is a higher order thing, and it's not a BS thing. It's not like just art and it just, you draw pretty pictures and it doesn't mean anything. It's that you are so seasoned and you're such a strong technologist that you can see it in your head, and then people like the patent committee can be like, yep, this will never work, and you can say, okay, give me a weekend, I'll show you it does exactly or almost exactly what I'm saying. And that's it really should be. If you're really an awesome software architect, I would argue that you should be able to, maybe this is a point of inspiration, you should be able to get to the point to where you can draw pictures like this that will take a while. Like this, I didn't figure this out in 5 minutes. This is me thinking on this for at least a few days. And keep in mind, this is like patent 117 or something, right? So there's a lot of iteration. If this were maybe my first patent application, this probably would have taken me hundreds of hours to get to this first thing. So this will take you some time, but then when you get to this, it should be that you can look at it and say, I'm pretty sure this will work. And that you can actually whip up a prototype and demonstrate that this works in a weekend. Like that's, in my view, if you're truly at the level of software architect the way that I see it, in terms of, like the Urs Muffs or the Linus Torvalds or the Tim Matsons, the Taylor Dolezals, any of those folks can figure this stuff out in their head. And then I can say, yeah, I don't believe you. And they can say, okay, give me a weekend. And they'll whip up the prototype. And then they'll show it to me on Monday. And it'll be like, do you believe me now? And I'll be like, yeah, I believe you now. And thanks for building up the prototype. I actually believed you the whole time. I just was kind of like gaming you. I was farming you to get you to just do some extra work on the weekend. Not that I would ever do that, Taylor, Urs, Paul. Okay, I think that's it for today, or that's it for this episode. I might actually do another and get into object-oriented programming next. Now that we understand a little bit of software architecture, I realize I went over some of this stuff pretty fast. I may revisit this. This is obviously a very complex topic. We've just scratched the surface, but hopefully this gives you enough of a basic idea to understand where software architecture fits in the hierarchy of software development, and when you might be experienced enough, when you may have put in enough time, you've put in your 10,000 hours, that you can now graduate to become like a software architect. Excellent. Feel free to leave any comments in the comments section, and thanks everybody. Happy Monday.